Hi folks! The following video is our last one on alkynes. I'll be discussing a final type of reaction known as alkylation, and then I'll talk about strategies for synthesis problems involving alkynes. Alkylation refers to installing alkyl groups in a molecule, alkyl groups being a general term for sp3 hybridized carbons. And the alkylation reaction is going to take advantage of the fact that a deprotonated terminal alkyne conjugate base can serve as a nucleophile in SN2 reactions with alkyl halides. Let's imagine wanting to do an alkylation reaction and starting with a neutral terminal alkyne. The base NH2- is strong enough to deprotonate this terminal alkyne. I can draw the two curved arrows of a proton transfer step. This would form the conjugate base, an acetylide anion. This anion could behave as a nucleophile, and it could react with an alkyl halide, where the carbon attached to the halide is an electrophile with a partial positive charge. In the SN2 step, I would bring in the nucleophilic acetylide anion to the carbon attached to the halide and break the carbon bond to the halide in the same step. This would generate a new carbon-carbon bond between the terminal alkyne's carbon and the carbon group attached to the halide. Let's consider a more specific example to start. Let's imagine starting with a 5-carbon alkyne. Notice this is a terminal alkyne, and I'm treating this with NaNH2 in NH3 solvent. The important part of the first reagent is the NH2-, which is a strong enough base to deprotonate the terminal alkyne. This generates the conjugate base, an anionic alkyne equivalent, that can behave as a nucleophile. And in the second step, I'm treating this molecule with an alkyl halide. In this case, a bromoethane molecule with 2 carbons. A new bond would form between the end carbon that would be anionic and the carbon attached to the halide. So overall, I would be adding 2 new carbons to the chain. These 2 carbons were present in the alkyl halide. Because the alkylation step is an SN2 reaction, it will only work well for methyl or primary alkyl halides. Recall that secondary or tertiary alkyl halides are not as good in SN2 reactions, and they will undergo elimination reactions instead. Here's an example of a synthesis problem involving alkylation. I'm starting out with acetylene, C2H2, and the final product is a 5-carbon alkyne. To the original alkyne carbons, I've added an ethyl group on the left and a methyl group on the right. To install these 2 different groups, I'm going to need 2 different alkylation steps. To first install the ethyl group on the left, I could treat the terminal alkyne starting material with the base NaNH2. This would generate the conjugate base that could serve as a nucleophile in an SN2 reaction with a 2-carbon alkyl halide. These 2 steps together give the alkyne alkylation. Because I used a 2-carbon alkyl halide, I've installed a 2-carbon group, which I've drawn on the left side of the molecule. Notice I still have a terminal alkyne CH bond present on the right side of the molecule, and this could be deprotonated and then the molecule treated with another alkyl halide. In order to install the methyl group shown on the right of my final product up above, I would use another treatment, first with the base NaNH2, and now in the second step, I would be using bromomethane, a 1-carbon alkyl halide instead. This second alkylation series would add the second alkyl group to the other side of the alkyne to give the final product. Note that in this synthesis sequence shown up above, I have two different alkylations, one with a 2-carbon alkyl halide and the other with a 1-carbon alkyl halide. The order in which I performed these alkylations didn't matter. So it also would have been totally fine to do the alkylation first with the 1-carbon bromomethane to give the following alkyne, and then follow this with the alkylation involving the 2-carbon bromoethane to give the final product. I now want to talk about synthesis strategies for converting between single bonds, double bonds, and triple bonds. To convert an alkyne into an alkene, you could use H2 with Lindlar's catalyst, or you could use sodium with liquid ammonia. You would choose which reagent you want if you want to make a cis or a trans alkene selectively. In this case, because I don't have a substituted alkyne, the choice of reagent doesn't matter. To go from an alkene to an alkane, you could treat the alkene with H2 in the presence of a metal catalyst like platinum. And instead, if you wanted to go from the alkyne all the way to the alkane, you could also use hydrogen in the presence of a platinum catalyst to go all the way there. Now let's consider, how do we go backwards? For now, I'm going to focus on going from the alkene to the alkyne. This can be done with a sequence of 3 steps. You start out by treating the alkene with Br2. You treat the formed compound with excess NaNH2, a strong base, and you follow that step with water. In these 3 reaction steps, first you're treating the alkene with Br2 to perform a halogenation reaction. This would add a new bromine to each of the carbons of the alkene to generate a dihalide product. Then you would have a sequence of 2 steps. First, treatment with excess NaNH2 to do a double elimination reaction. Then treatment with water to go from an anionic intermediate to the neutral alkyne final product. The one thing we can't fill in this diagram at this time is going from an alkane to an alkene, and for this we're going to need reactions that we'll see in a future chapter. But largely, except for this section, we now have a lot of reactions for interconverting or going back and forth between single, double, and triple bonds. One thing you're going to look out for in synthesis problems is whether or not your starting material and product have the same number of carbons. So I want to highlight 2 reactions that we do that change the carbon skeleton, meaning adding or subtracting carbons from the molecule. The only reaction that we've learned so far that increases the number of carbons in a molecule is alkyne alkylation. Let's imagine starting out with the conjugate base of a terminal alkyne featuring 4 carbons. This could serve as a nucleophile to attack a 3-carbon alkyl halide. In the alkyne alkylation, the deprotonated alkyne serves as the nucleophile in an SN2 step. And in the product, I've added new carbons to my original molecule. So when I added these 3 new carbons from the alkyl halide on the right, I've increased the number of carbons in the molecule from 4 to 7. And so far, we've only learned one reaction that can break carbon-carbon bonds, and that is ozonolysis, either of an alkene or an alkyne. Here, let's imagine starting with a 5-carbon alkene. In this case, the alkene is placed between the 2 right carbons. I'm treating this with ozone followed by DMS. The ozonolysis will completely cleave the bond between the 2 carbons of the alkene. The ozonolysis of an alkene will generate new carbon-oxygen double bonds. And based on the starting alkene placement, notice I went from a 5-carbon molecule to one molecule with 4 carbons and one molecule with 1 carbon. So I was able to shorten the length of a carbon-carbon chain using ozonolysis. When approaching a synthesis problem, I recommend thinking about 2 things. First, is there a change occurring in the carbon skeleton, meaning either the arrangement of the carbons or the number of carbons? And next, thinking, is there a change occurring in the identity or the location of a functional group? As an example, let's consider the following synthesis problem. I'm starting out with a terminal alkyne, and in the product I have a trans alkene. I recommend starting by numbering carbons to know how many of them there are, and also on which carbons the functional groups are placed. The starting material has 5 carbons, with the alkyne present between carbons 4 and 5, as I've numbered this. This isn't naming style numbering, this is just for me to keep track of positioning. And in the products, I have 7 carbons instead of 5, and notice the alkene is present between carbons 4 and 5. Before starting, I want to consider a couple of things. So notice that my number of carbons has changed here from 5 to 7. So I need to consider what reagents and reaction could I use to add 2 carbons. The only reaction we've learned so far for increasing the number of carbons in a molecule is alkyne alkylation, so we will need to use that step. We'll also need to consider how do we go in some step of the reaction from having an alkyne to having a trans alkene. The reagents for this step are treatment of the alkyne with sodium in the presence of liquid ammonia. Since I need an alkyne present in order to have the alkylation reaction, I need to perform the alkylation step first before converting my functional group into an alkene. For the alkylation step, I would treat the terminal alkyne first with a strong base, sodium amide, and second with an alkyl halide with the number of carbons that I want to add. Since I want to add 2 carbons, I would use a 2-carbon alkyl halide. This step would generate a 7-carbon molecule. The alkyne is still present between carbons 4 and 5. And now, looking back to my final product, I need to convert that alkyne into a trans alkene. I would do this by treating the alkyne with sodium in liquid ammonia. So in this example synthesis problem, I did have a change in carbon skeleton that required me to add carbons. The only way to do this was alkyne alkylation. And then I had a change in the identity of a functional group, but not its location. It was between carbons 4 and 5 in the chain in both cases. But I did need to manipulate the functional group by converting it from an alkyne into an alkene. As synthesis problems become more complex, a useful tool for approaching them is known as retrosynthetic analysis. This is essentially thinking backwards through your synthesis rather than forwards. Often it will be very useful to begin by identifying the last step in the synthesis. An example where I think this is helpful is starting out with an alkyl halide and having this product which is a ketone. First, I want to evaluate the carbon skeleton of my starting material and product. I have a 3-carbon alkyl halide starting out, and I have a 5-carbon ketone in the product. By seeing that the number of carbons has increased, I know that my reaction sequence will need to involve alkylation of an alkyne. Now I want to look at what functional group is present in the product, which would be a ketone. And one method for making ketones that we've learned so far is using mercury catalyzed hydration of an alkyne. So, thinking backwards one step in the synthesis, I want to think about what alkyne would I need to treat with mercury-catalyzed hydration conditions to get to this 5-carbon ketone, where the ketone is second from the right. Because mercury-catalyzed hydration has Markovnikov selectivity, I would want my alkyne to be present between the 2 carbons on the right side of the molecule, so that I would add the hydrogens to the less substituted carbon and convert the more substituted carbon of the alkyne into the ketone. Because the ketone I want has 5 carbons, the alkyne before that has 5 carbons as well. Now I want to think back further, knowing that I started out with a 3-carbon alkyl halide. How could I convert this molecule into this 5-carbon alkyne? A way I could do this, which would add 2 carbons to the molecule and install the alkyne functional group, is to treat the alkyl halide with this anionic conjugate base of an alkyne, where I have a CH bond on the other side of it. This anionic molecule could serve as a nucleophile to attack the alkyl halide in an SN2 type step to generate that alkyne that I want. So overall, in my synthesis, I wanted to convert an alkyl halide into an alkyne in a way that added 2 carbons to my molecule, and then I wanted to convert that alkyne into a ketone, a step that maintains the number of carbons. I found it useful to start by thinking about the last step of my synthesis first, and then fill in the gaps from the starting material I was given to that last step. As a final example for demonstration in this video, consider the following reaction. I start out with an alkene, and the product is an aldehyde. First, I investigate the carbon skeleton of the molecule. Notice that my starting material contains 5 carbons, and my product contains 5 carbons as well. So the carbon skeleton has not changed in this reaction. What this indicates to me is that neither of my reactions that change the carbon skeleton are necessary. So I don't need alkylation of an alkyne or ozonolysis. A functional group present in the product that isn't there in the starting material is an aldehyde. And a method that we've learned for making aldehydes in a way that doesn't change the number of carbons present is hydroboration oxidation of alkynes. This gives an anti-Markovnikov addition to give a less substituted aldehyde product. I would recommend starting by thinking in reverse, in a retrosynthetic manner from the aldehyde product. So you could imagine starting out with an alkyne before the last step and treating it with hydroboration oxidation conditions to generate an aldehyde. What you would want is your alkyne present between the carbon of the aldehyde and the carbon attached to it. This is that structure of the alkyne you would want going into the final hydroboration oxidation reaction to install that aldehyde functional group. And now we need to figure out how do we get from our starting alkene to the following aldehyde in a way that doesn't change the number of carbons present. Earlier in this video, I discussed a method for doing this. What you would want to do is start by treating the alkene with Br2 to generate a dihalide intermediate. You could then treat this dihalide with excess NaNH2 followed by water to do a double elimination and make the terminal alkyne. So in this synthesis as well, I started by investigating the number of carbons in the starting material and product carefully. I then looked at the functional groups present. I worked backwards a step to figure out what molecule did I want going into the final step of my synthesis, and then I filled in the gaps from the starting material to that intermediate. Okay, so in this video I introduced one new reaction called alkyne alkylation, which is a useful way of extending the number of carbons in a molecule. The rest of the video highlighted some considerations for synthesis, either changing between single, double, and triple bonds between carbons, discussing strategies to increase the number of carbons or decrease them in a synthesis, and then I demonstrated a few examples of solving synthesis problems, where I recommend doing one step in reverse and then working forwards. That's it for this video. I will see you in class.